Good morning, good afternoon, or good evening, whatever time you're watching this educational video. Today, this moment, we will be discussing about the electric field. So I provided two problems related to the electric field that you can uh, watch in order for you to practice on your own on how to solve problems related to the field. The first problem, what is the magnitude or value of a point charge that would create an electric field of 1 Newton per coulomb at a point 1 meter away? So in this problem, the value of the E field is given. It's 1 Newton per coulomb. And the distance or the R is also given. It's 1 meter away. So we will try to find out the magnitude of that point charge releasing the 1 Newton per coulomb electric field. As we all know, a charged particle can generate E field. Okay, and the distance from that point charge is 1 meter away. So let's try to find out the coulombs of the point charge. Our equation is this: F is equal to QE. F is the electric force, that's Newton. Q is the charge, the unit is coulomb. And then E is the electric field, Newton per coulomb. But we cannot use this equation, because we have a variable of R here, or the distance, and we do not have distance in our equation here. So we will try to integrate or relate Coulomb's equation to this equation, F is equal to QE. As you can still recall, the Coulomb's equation is F is equal to Coulomb's constant, product of the two charges over R squared. So we will gonna uh, substitute this equation to our F here. Okay, so we can have this new equation now. So the force becomes, we substituted this equation, or yeah, equation a while ago. So we can have this new formula now, derived formula. And we already have R, so we can substitute 1 meter in our problem. Okay, and we cross multiply. That's why we have this new equation here, because we just cross multiply QE by R squared, and then we have an imaginary 1 in the denominator here, and we can cross multiply it with K and the product of the charges. So you can have this new equation. Remember that the uh, Coulomb's constant in a vacuum, since it happens in a vacuum, it wasn't stated, but yeah, it is, commonly happening in vacuum. So the value is 8.99 times 10 raised to 9 Newton meter squared per coulomb squared. Okay. The next thing we do in my presentation, I want to isolate electric field here, but yeah, you can just have another way on what particular variable you're trying to isolate. So in my case, we will isolate electric field by dividing R squared Q both sides. So if you notice, we have R Q, R squared Q, and then we divide it by R Q, R squared Q on the other side. We can cancel the charge one here, you notice, and then we also cancel the uh, R squared Q on the left side, isolating the electric field. So we have this uh, derived formula to get the E field. We integrated the Coulomb's equation in FQE equation. So in that case, we will use this to solve problem A. So solution, here's our formula here, the derived one. We can substitute. We have the value of E. We have also the value of K. It's the Coulomb's constant in a vacuum. We don't have the value of charge, but we have the value of our R. So we can substitute them perfectly in our equation. So we have 1 Newton per coulomb, that's the electric field, 1 meter, that's the distance, and then we have the Coulomb's constant in a vacuum, 8.99 times 10 raised to 9 Newton meter squared per coulomb squared. We can cancel out units here. Okay. Uh, we can cancel the Newton meter, and then we can also, yeah, we will, we will, hold on. Yeah, 8, 8.99 times 10 raised to 9. We don't have the value of charge yet. And then we will divide it by 1 so we can have the value, same value. And the next thing we should do is to divide both equation by this magnitude here. It's 8.99 so that we can cancel it out. You also have to divide the other equation with the same value. We can cancel this value here, same, because 8.99 times 10 raised to 9 divided by same magnitude will result to 1. So we isolated here Q because that's the goal. And then we can cancel the unit newtons um, on the other side. Then the 1 coulomb also, we can cancel the 1 coulomb. We have coulomb squared here, and then we can cancel out coulombs uh, in the numerator and 1 coulomb in the denominator. So 1 divided by 8.9 times 8.99 times 10 raised to 9, it will give you this answer. It's 1 times 10 raised to negative 10 coulombs. That's the value of the magnitude of the point charge that generates 1 Newton per coulomb electric field 1 meter away. Okay. Another problem we have, a point charge is 4 times 10 raised to negative 6 coulomb is located at a certain point in space. So it's very obvious we will be using the Coulomb's constant in a vacuum in this problem. Let's figure out the magnitude of the E field at 0.2 meters away. And then figure out the force due to the E field or point charge on a test charge Q that is 2 times 10 raised to negative 6 coulombs. So we will try to visualize what's going on in this problem. We have a source charge or a point charge, and then since it is a charged particle, it generates electric field. Yeah, I just drew, or I just put it that way. Although it's symmetrical and like it will form a circle, but this time I just focus on that part of the E field, and then um, it's 2 meters, 0.2 meters away, and we have a test charge there. So let's try to figure out the E field, the value of the E field coming from our source charge. And we'll try to find out the force experienced by the test charge due to the electric field. So first and foremost, we will have to find the magnitude of the E field of this source charge or point charge. So it's in the vacuum, we will be using this constant here. Okay, so the same formula, we'll substitute everything correctly. So we have the value of K here, and then we have the value of our point charge. It's positive, and we will divide it by R, or it's the distance, 0.02, and don't forget to square it out, okay? And then when you plug it on your calculator, yeah. But before that, I will show you that we can cancel the units here, Newton meter. Sorry, not the Newton meter, but the meter squared. And we can also cancel this coulomb here and just 1 coulomb of our coulomb squared. Okay. And then plug it all in your on your calculator, so it will give you this answer. In the numerator, you will have 35960 Newton per coulomb, and then 0 point, it's not, oh, hold on. I'm very sorry. In the problem, it's 0.2. Yeah, it's not 0. It's not 0.02. So you will have this correct answer here in the denominator. It's 0.04. Again, it's 0.2, not 0.02. Okay? And then if you will divide it, you will get a quotient of 8.99 times 10 raised to 5 Newton per Coulomb, or we can follow the sig fig here since we have one sig fig is our limiting factor. So it must be that we have one sig fig in our final answer. Okay. So yeah, that's it. That's the electric field generated by our source charge or point charge. Now let's try to find out the force experienced uh, by this test charge. We will be using this formula. Um, yeah, this will be our test charge here in the electric field that we calculated a while ago. So we can substitute them, the values. It's 2 times 10 raised to 6, and then multiplied by, yeah, I just used this approximation, 9 times 10 raised to 5 Newton per Coulomb. We can cancel Coulomb here, so we can have 1.8. If you will multiply these factors, you will have 1.8, or if you will follow the sig fig, so you will have 2 newtons here. Uh, that's the force experienced by the test charge due to electric field passing on the test charge. It is the Coulomb's force experienced by the test charge. It's the Coulomb's force because the field is coming from a single particle or charged particle. If it comes from a single point charge or any single charged particle, the electric field will be the Coulomb's force per unit of charge. Okay, and you can also use the Coulomb's equation to solve this problem, and you still get uh, this magnitude of the force. All you have to do is to use the Coulomb's equation. You have the value of K multiplied by charge 1, and then charge 2. Charge 1 will be the point charge. You can have it as your charge 1, and then you can have it as your charge 2. Then you will divide it by r squared. That's our Coulomb's force. You will still arrive at the same answer. You can comment down below if you arrive to this answer. Thank you. And that's it. That's it for this moment. Thank you so much for watching. And yeah, it's not conduction. It's not anymore electrostatic that we are discussing here. It's the E field. I'm very sorry. I forgot to edit the title. Thank you so much. And if it helps you, I hope you will like, share, or subscribe. Yeah, this is in that way you're showing uh, that is a good point for me to do more of this. Thank you so much and have a great moment. See you around until next time.